Hey everyone, and welcome back for another deep dive. Today we're going to be stepping into the lab, well, the really cool kind of lab.
The ones with the bubbling beakers and the lasers.
Exactly. We're going to be exploring the cutting edge of molecular catalysis with some excerpts from the August 30th issue of Science, hot off the presses.
And this isn't just some obscure sciencey stuff. We're talking about the kind of research that quietly shapes so many aspects of our lives, like every day.
You're totally right. Pharmaceuticals, agriculture, material science, molecular catalysis is the secret sauce behind so many things we kind of take for granted.
It's like the ultimate example of how these seemingly abstract scientific concepts can end up having this huge, but often invisible, impact on all of us.
And speaking of impact, we've got to talk about Professor Eric N. Jacobson from Harvard. He just won the 2024 Welch Award in Chemistry. Huge honor.
Absolutely. Jacobson's work is truly groundbreaking. What's so remarkable is his development of these things called metal sailing complexes. They sound super complicated, but basically...
They're not something I'd want to try and make at home.
Probably not. But they've really revolutionized how we approach certain chemical processes, you see. Just imagine you need to build a molecule, right? But it can exist in two mirror image forms, and only one of them is useful.
Okay, I'm picturing like those trick mirrors where one side reflects normally and the other makes you look all wonky.
Exactly. It's kind of like that, but on a molecular scale and with real consequences. So Jacobson's work essentially gives us the tools to separate those mirror images and isolate the exact one we want. It's about control at the most fundamental level.
That is seriously impressive. We're talking about creating medicines or materials with a level of precision that was basically impossible before, right?
Exactly. And get this, Jacobson's findings have had this ripple effect throughout the whole field. This issue of Science features highlights from the Frontiers in Molecular Catalysis conference. It's basically like the Super Bowl of chemistry, and Jacobson's influence is everywhere you look. It's really cool to see.
Okay, I'm already geeking out and we haven't even gotten to the conference yet. What were some of the big, mind-blowing takeaways? Give me the highlights.
So one of the huge themes was this idea of directed evolution. Now, you might be thinking, wait, isn't evolution something that happens over, millennia?
Yeah, I mean, that's what I learned in school.
Right. And you'd be totally right. But Frances Arnold, she actually won a Nobel Prize for her work in this area. She figured out this incredible way to harness the power of evolution in the lab, essentially speeding up the process of developing new enzymes.
Wait, hold on. Back up a second. We're talking about creating new enzymes, those protein powerhouses that drive tons of biological processes, but in a lab.
Exactly. And it's not just some cool science trick. This breakthrough has the potential to lead to cheaper, more effective medicines, develop more sustainable manufacturing, even lead to big advances in biofuel production, things that impact us every single day.
That's mind-blowing. Okay, so directed evolution, definitely a game changer. What else did this chemistry Super Bowl reveal?
Another major focus was on asymmetric catalysis, and this one's a bit tricky to explain. Imagine you need to design a glove that fits your left hand perfectly.
Okay, got it.
Now imagine trying to do that, but at the molecular level. That's kind of what we're talking about with asymmetric catalysis, using catalysts to selectively create one specific mirror image molecule over its twin. And it's super important for drug development because even the tiniest change in a molecule's structure can totally change how it behaves in the body, completely.
So we're talking about taking control of chemical reactions at this amazingly precise level, making sure we get the exact molecule we need and not its evil twin.
You got it.
Yeah.
And the really cool part is that scientists are using all sorts of sophisticated tools to reach this level of control. For example, data science is now playing this huge role in designing new catalysts and predicting how they'll behave.
Data science and chemistry. Who would have thought?
I know, right? It's this fascinating intersection of, traditional chemistry and cutting-edge technology. But even with all the fancy tech, the fundamentals of physical organic chemistry are still as important as ever.
So it's not just about knowing how to crunch the numbers, but also really understanding the underlying dance of the molecules themselves.
Absolutely. And let's not forget about biocatalysis. It's all about using nature's catalysts enzymes to do chemistry in a cleaner, more efficient way.
Basically letting nature do what it does best.
Exactly. And the conference highlighted some really exciting innovations in this area, like with electrochemistry and high-throughput experimentation. Basically finding ways to run thousands of experiments at once to speed up discoveries.
Now that's what I call working smart. Okay, so we've got all these incredible advancements in molecular catalysis, but with all this talk of chemicals and reactions, there's got to be a big environmental angle to all of this, right?
You're totally spot on. Sustainability is a huge, like, unavoidable part of this whole conversation. And it kind of leads us perfectly into this intriguing and potentially controversial area of research. Seaweed farming, but like for carbon capture.
Okay, seaweed farming. I've heard people talking about this, but how does it connect to carbon capture? Help me wrap my head around it.
Okay, so picture this. Massive, like underwater forests of seaweed, just soaking up carbon dioxide from the water as they grow. Now imagine we strategically cultivate these seaweed forests and then, get this, we sink the mature seaweed down to the ocean floor.
Oh, and we just send it down at the ocean depth. Like, is it some kind of sunken treasure?
Kinda. Except this treasure is all about, fighting climate change. You see, when the seaweed breaks down on the ocean floor, the carbon gets trapped, potentially for hundreds of years.
So we're talking about a natural system with this built-in carbon storage mechanism.
Precisely. Proponents argue it's this amazing way to use ocean space, right? We don't need to use land or freshwater resources. Plus, it's this elegant way to lock away that excess carbon we've been pumping into the atmosphere.
It sounds like this win-win, at least, at first glance.
Yeah.
But I know there's always another side to the story. What are the downsides, the what-ifs?
You're totally right to be a little skeptical because, honestly, there's a lot we're still trying to figure out. One big concern is this idea of carbon leakage. As the seaweed grows and decays, some carbon might escape back into the water.
So it's not a totally closed loop then?
Okay.
But how much leakage are we talking about? Is it like a drop in the bucket, or should we be seriously worried?
Well, that's what researchers like Kristen Davis and Chance English are trying to nail down. They did this really interesting study on carbon leakage from, the big seaweed, and it's shedding some light on this exact issue. What they're finding is it's way more complicated than we thought.
Science is usually like that, more questions than answers.
Exactly. Their research shows that the rate of leakage, well, it can vary a lot depending on things like the type of seaweed, the ocean conditions. It's complex.
So we need more research to really understand the full carbon accounting of this whole process, how much actually gets stored versus how much leaks back out.
Exactly. And then there's the impact on the deep sea ecosystem itself.
Yeah.
We got to think about that too.
Right, because dumping tons of basically fertilizer on the ocean floor has to have some effect, right?
Of course. I mean, that's a whole ecosystem down there. David Siegel has done some fascinating work on this, looking at the ecological impacts of seaweed deposits. What he's found is it's a mixed bag, really.
Like some species might benefit while others, not so much.
Yeah, exactly. Some species might thrive in these like newly enriched environments, while others, get crowded out or even disappear.
So it's a trade-off trying to find that balance.
Exactly. But what's encouraging is that at least we're asking these tough questions and the research is being done.
Right. It's not just blindly jumping on the latest trend.
Precisely. Speaking of jumping in, are there any companies actually trying to, make this seaweed solution a reality?
Yeah, that's what I'm wondering. Are we just talking about this in theory, or is someone out there actually growing these underwater forests?
There are. Ocean Rainforest, they're a company based in the Faroe Islands. They're doing some really interesting stuff with seaweed cultivation. They're exploring all sorts of applications, food, animal feed, even cosmetics.
So it's not just about carbon sequestration. Seaweed's got range.
It really does. But yeah, they're also looking at the carbon angle. It's a big part of their research.
It's interesting how this seemingly simple organism, seaweed, can be at the center of such complex scientific, environmental, and even economic discussions.
Oh, absolutely. And this whole idea ties directly into the world of carbon credit markets. That's where things get really interesting.
Because if you can successfully capture carbon with seaweed, could you then sell that credit to other companies trying to offset their emissions?
Exactly. It could be a huge financial incentive for companies to get on board with this whole seaweed thing. But, of course, the whole idea of carbon markets, whether they actually work, whether they're fair, whether they're actually helping, well, that's a whole other can of worms.
A whole other deep dive for another day.
For sure. For now, I think we can agree that seaweed farming for carbon capture definitely has potential. It's promising. But we got to approach it carefully, keep asking those tough questions, and make sure everything we do is responsible and sustainable. Otherwise, it could backfire.
So it's a wait-and-see kind of situation. Exciting, but with a note of caution.
Exactly. Now, speaking of exciting discoveries, this issue of science also had some mind-blowing archaeological stuff.
Like what?
They talked about this 6,000-year-old structure in Spain called the Dolmen of Menga. Ever heard of it?
Oh, yeah, the megalithic structure, right? With those massive stones, like prehistoric engineering at its finest.
Yeah. And that's what's so cool about it. This structure, they built this thing with only primitive tools,
Yeah.
but it shows this level of architectural, like, genius.
Mm-hmm.
It's making us rethink what we thought we knew about prehistoric societies.
It really makes you think, how could they design and build something so complex, so long-lasting, without, modern technology or even a written language?
Right. It's incredible. And then on the total opposite end of the spectrum, there was this article about something much smaller, but just as significant microplastics.
Microplastics, we hear about those everywhere now. Not exactly a good sign, is it?
Nope, not at all. We know these tiny plastic particles are basically everywhere, from the highest mountain to the deepest part of the ocean. It's nuts. But this article in Science highlighted this scary thing. Microplastics are actually messing with these things called biogeochemical cycles.
Okay, now that's a mouthful. Biogeo what?
I know, right? Sounds complicated, but it's actually pretty simple. These are the fundamental processes that control how stuff like carbon, nitrogen, phosphorus, the elements that make up everything, how those elements move through the environment.
So we're not just talking about, like, plastic pollution being an eyesore. We're saying these microplastics are messing with the basic building blocks of our planet.
Pretty much. And this is where it gets really worrying. These tiny plastic bits can mess with how plants absorb nutrients. They disrupt the food chain, even change the composition of microbial communities in the soil. It's a cascade effect. One change triggers another and another.
Yikes. I knew microplastics were bad, but this is next level bad.
It's a serious issue, no doubt, and it makes us think about the bigger picture of what we're doing to the planet.
Right, even the tiniest actions can have huge consequences. And speaking of actions and consequences, wasn't there an article about government-funded research and patents?
Oh yeah, that's right. That's an issue that needs way more attention. Basically, there's this trend where patents that come from government-funded research, they often don't even mention the government's role in their development.
So taxpayers are funding research that then gets patented by private companies who then reap all the profits.
Yeah, basically. And it raises all sorts of questions about, fairness, transparency, and whether the public is actually benefiting from the research they paid for.
Because ideally, shouldn't those benefits trickle back down to the public in some way, like cheaper medicines or, I don't know, faster internet?
You think so, right? That's the whole point of publicly funded research. Some people say we need stricter rules around intellectual property for this kind of research, while others say it's more about fostering this culture of transparency and collaboration between universities, companies, and the government.
Yeah, because science shouldn't be about, like, who gets the patent, but about making life better for everyone, right?
Totally.
Yeah.
And the more we talk about this stuff, the more light we shine on it, the better chance we have of finding solutions that work for everyone. 100%. The more we talk about these things, the more we shine a light on it, the better chance we have of, finding solutions that actually work for everyone, not just like a select few.
It's all about keeping science open and accessible, right?
Yeah.
So it can benefit all of humanity.
Exactly. And it kind of brings us back to that Dolmen of Menga thing we were talking about earlier.
Oh, yeah. The prehistoric builders. It's just crazy to think that they could create something so sophisticated without all the tools and technology we have today.
I know, right? It really makes you wonder, like, what else is out there? What other scientific knowledge or technological advancements did ancient civilizations have that, we've just completely lost track of over time?
It's like, what if we're not actually discovering new things, but just rediscovering things that were already known thousands of years ago?
Yeah.
It's kind of humbling when you think about it.
It really is. It makes you realize how much we still don't know about the past and, about our own potential. Like, what are we capable of achieving if we really put our minds together and, like, tap into that same ingenuity that built the pyramids or Stonehenge?
That's a really good point. It's not just about looking back, but also about learning from the past and using that knowledge to create a better future.
Exactly. And that's what makes these deep dives so interesting, right? We get to explore all these different aspects of science and technology, from the tiniest molecules to these ancient megastructures, and it's all connected.
It really is. Well, I think that's a great place to wrap things up for today. We've covered a ton of ground in this deep dive, from molecular catalysts to seaweed farms to, the mysteries of prehistoric engineering. It's been quite a ride.
It really has. And, it just goes to show that science is everywhere if you know where to look. It's not just something that happens in a lab somewhere. It's shaping our world in countless ways every single day.
Couldn't have said it better myself. A huge thanks to everyone for joining us on this journey of discovery.
Yeah, thanks for listening, everyone. And be sure to tune in next time for another exciting deep dive into the world of science.
Until then, stay curious.